Okay, today we're looking at our last section on graph theory, which is matching of bipartite graphs. Okay, so let's see what it's all about. We are given a bipartite graph. Now remember, a bipartite graph is a graph where the edges in the graph has been subdivided into two distinct sets, such that the edges in set 1 is non-adjacent to the edges in set 1. And the same goes for set B. They are only adjacent across the sets. Then it's a bipartite graph. Okay, so the question is, if we have a bipartite graph, then a matching is a subset of the edges for which every vertex belongs to exactly one of the edges. So meaning that we're only looking at edges here when we're matching in bipartite graphs. And as we select edges, we are not going to repeat vertices. Okay, so vertex in one set cannot belong to two separate or to two edges, or cannot be part of two edges which are mapped into the other set. Okay, so unique mappings here. Now, not all bipartite graphs have mappings, they say, but let's look at the graph that we have on the screen and let's see how many matchings we can find. Now I've drawn them here, the graph. I'll do a mapping over here, and all the vertices, there's 6 vertices at the top, 6 at the bottom, so there's an even amount or an equal amount of vertices in the one set and the other set. Okay, notice that this is not a complete graph. Okay, it is a graph where not all the vertices are joined with one another. Okay, so let's have a look. If I delete my black edges that are left in my graph, so I'm going to select all the black edges and I'm going to delete them, and then let's just hide them. Oh, there's one that I forgot to hide, and that's that one. Let's hide that one. Then we can see that every vertex is connected to one and only one edge as we move from set 1 to set 2. If we do the same for the second graph, then we can see that there is another matching which works. So if I hide those segments, look at that. There's no vertices that's belonging to two edges, or no two vertices are belonging to the same edge from set A, and the same from set B of vertices. So let us do the quick one for the bottom. Let's quickly get rid of these dark sides. Now I'm using Sketchpad for this because it's quite nice to illustrate these in Sketchpad, and you can see there's mappings or matchings, to use the graph theory language, for each one of these. Now let's see if we can find another one. So I'm going to select, let's say I select from here to the sets at the bottom. So I'm going to select this side. So let us select the two vertices as well, and let's color that blue. Okay, so I can't use those anymore. So I go to the next vertex. The only selection I can make is those that side over there. Why is that the case? Because if I went back to this vertex, I would have used, or to that edge, I would have used this vertex more than once. Okay, so I go to the next vertex. The next vertex, I can pick one of the two. I might change my mind later. I can't pick this one because this vertex will then belong to two edges. So I'm choosing those two and I'm coloring it blue, and we can see there's 1, 2, 3 vertices left. If I go to this vertex here, it only goes to that vertex via that edge, or it maps to this vertex via that edge, which is not allowed. So at this point I'm going to change my mind about this side, and I'm going to color it back into black. Okay, so I'm going to connect those two immediately because that's the only option that's left for that vertex. Now if I go back to this vertex, I cannot use that one, I cannot use this one. So the only combination that I can match it with is that set over there. Okay, so hopefully the rest of them we can do the same. So let's go to this vertex. I cannot move there, but I can match it with that vertex via that edge. So that is a unique match. And then this is the last match that we can see obviously will work. Now let's hide our black lines so we can see exactly how many or how different this is from all the vertices that we have matched with edges so far. Okay, so there we see it's a different matching, but all of these matchings are indeed unique. So we have what we call a perfect match. Okay, so a perfect match uses the number of vertices divided by 2. So there's 12 vertices here, so it uses 6 edges. Okay, the number of edges that a perfect match uses is the number of vertices halved. Okay, so let's see. This was quite nice. We did the same thing for the same graph all the time. So let's have a look at this graph over here. I'm going to change it all back to the same color and we can try and find the matching. So if we look at this vertex, the only vertex it can visit is this one via that edge. So I'm going to change this to a color of pink. The next one I'm going to look at is that vertex, which can only match with this one via that side, because the other vertex that it is paired with has already been used. Now this vertex goes there and there. These two have been used, so it can only match with the third vertex. And now I find myself in a situation because this one has already been used. It's target vertices on the other set, and that one has already been used. So this one does not have a matching. The bipartite graph there does not have a matching, and we need to think why that is the case. The third one here, I've come back and I've looked at all of these vertices. If I hide, well, it doesn't help to hide the black vertices or the black lines because there's 2 vertices not used. The only mapping I could use there is that. I've used it over there and I've used the other path over there. No matter how the paths look like, what the paths look like that I'm using, there's always a vertex pair that's going to be left open. Now that is also very interesting, and we need to think about indeed why that is the case. So let's go back and let's carry on reading. Okay, it says, suppose we have a bipartite graph G. A matching of set A is a subset of the edges for which each vertex of A belongs to exactly one edge in a subset, and no vertex in B belongs to more than one edge in the subset. In practice now, it says we will assume that the cardinality of set A is equal to the cardinality of set B. The two sets have the same number of vertices. So this says that every vertex in the graph belongs to one edge in the matching. Some context might make it easier to understand. Think of the vertices in the one set as representing the number of students in a class, and the vertices in the other set, the presentations, that topics for presentations that they must choose. We put an edge from every vertex A that belongs to the student set to a vertex B, which belongs to the set of topics that the students must choose. Of course, some students would want to present more than one topic or want to choose from more than one topic. So the vertex will have a degree higher than 1 at that point. The vertex in B, clearly. Okay, so as a teacher, you want to assign to each student their unique topic. Let's just make sure we understand what they say over here. Now this is about matching. What we are calling matching in this book is sometimes called a perfect match or a complete match in other books or in other videos or wherever you find information. This is because this is because in it interesting to look at non-perfect matchings as well. I'm sure that should say is. We call these partial matchings, but we won't be looking at that in as much detail. Okay, so thus, you want to find a matching in A, you pick some subset of edges so that each student gets mapped up with exactly one topic, and no topic gets matched to two students. Then you have what we call a perfect mapping. The question now is, when does a bipartite graph have a matching or a perfect matching of set A? Now folks, we're going to answer that question by looking at cases when it doesn't contain a mapping. Okay, so let's look at the first case here. A vertex A is not adjacent to a vertex B. So in this case, there's no edge that connects this vertex to a vertex in the next set. Then it doesn't contain a mapping of S. Now the notation, let me just talk about this notation. This is the set S, and we're going to introduce the language now, but this is the neighborhood of S, meaning that S can have that as a neighbor, or this vertex as a neighbor. So it can be mapped to three vertices in the other side, but we only want to choose one of them. But S has one element in it, the subset of this is 1, and then it is mapping, so the subset of those vertices, in other words its neighborhood, consists of 3 vertices, which helps. Okay, the next one says if 2 vertices in a set A are adjacent to the same vertex in B. Now there's 2 vertices and they both map onto the same vertex over here. Now that's a problem. They don't map onto anything else. So if we assign this edge to those 2 vertices, then this one will have a problem. It's equivalent to setting its degree like here. The degree of that vertex was 0. We cannot use this edge again, so it's equivalent to saying this degree of the vertex over here is 0. So that's the second one where we will have a problem finding a mapping. The first, if there's no edge from a vertex. The other one, if 2 of the vertices go to the same vertex in the other set. Now let's just think about what that means in the example that we just spoke about. Students choosing topics. That means that 2 students want to present the same topic. And we can't have that. Each student must present a different topic. So there's no matching in that graph. The third case is if 3 of the vertices in A, this set over here, are adjacent to 2 of the vertices in B. Now that is quite obvious for the same reason as what we have here. If we assign that set to those 2 vertices and we assign this edge rather to those 2 vertices, then we've used both of the vertices in the neighborhood already. So this third vertex is not connected, cannot connect, like it could not connect here. It could not connect to a vertex in the other side. So if there's a group of n students who like to make n-1 or less choices, then the matching is impossible for us to find. Okay, so let's see. It should be clear at this point that if there is let me read that again. It should be clear at this point that if there is a group of n students, who, as a group, would like n-1 or fewer topics, then no matching is possible. That's what our third graph showed. This is true for any value n and any group of students n. So to make this more graph theoretic, say that we have a set S, which is a subset of vertices A. We define NS to be the set of all the neighbors of vertices in S. So NS are the neighbors of S. S is a subset of A, and then NS clearly will be a subset of the second set B. That is, NS contains all the vertices in B which are adjacent to at least one of the vertices in S. In the student or topic graph that we've just spoken about, N of S is therefore the set of topics and S represents the set of students. Now here we have our very first theoretical thing to think about, the matching condition. If a bipartite graph G, which has two sets of vertices, the vertices A and the vertices B, has a matching of A, we want to match the students with the topics, then the topics must be at least the cardinality of the topics, meaning the amount of topics that we make available must be at least the size or the total of the number of students that are available. So the cardinality of the set S, at least or more. So we can have more topics and fewer students to choose those topics. That will work. But we can't have that the other way around, because then there's less topics than what there are students, and students cannot choose the topics. So the question then becomes, is the converse true? So in other words, if you have more topics than students for all students, which is a subset of the student set, every set of vertices has at least as many neighbors than the vertex in the set. Does this now mean that there is a matching? And yes, indeed it does. The obvious necessary condition is also sufficient. Okay, now that is the condition that we have over here. This is the theorem that was first proved. Now look at how recent this theorem was stated and proved, folks. It just shows you the relevance of graph theory in our lives today. Okay, that is Hall's marriage theorem. Now they chose that because it was called Hall's marriage theorem. In the past it was related to the marriage between a man and a woman with no polygamy involved. So to be politically correct, we used the idea of students choosing topics. Okay, so let G be a bipartite graph. That's the first condition. With sets A and B. Then G is a matching of A. If and only if, a biconditional statement. The neighborhood of S, where S is a subset of A, is at least as big as the set A. So the cardinality of the neighborhood is at least the same as the cardinality of the subset that we are choosing from. Now folks, we're going to look just now at a few of those examples where we actually see where we apply Hall's marriage theorem strictly. We look at cases that violates that. First example we've got here is example 4.6.2. It says, suppose you deal 52 regular playing cards into 13 piles of 4 cards each. Now folks, what does that mean? If your cards are sorted, all the clubs together, all the spades together, etc., there's 13 cards in a suit, in a 52 pack. So if you have the suit packed out and beautiful, 1 card per suit here, you have 13 packs with 4 cards each because there's 4 suits. Okay, so for those of you that don't know playing cards, prove that you can always select one card from each pile to get one of each of the 13 card values from an ace to a king. Now folks, just think about this. If a suit has 13 cards and you've spread the suit, each card in a pile, then you spread the next suit, each card in a pile, it makes sense that that is going to be the case. Now let's see. Doing this directly would be difficult, but we can use matching condition to help. Construct a graph with 13 vertices in set A, each representing one of the 13 card values from ace to king, and 13 vertices in set B, each representing one of the 13 piles. There's 4 suits, so each pile will have 4 cards. So draw an edge from each vertex in A to a vertex in B, if a card with value A is in pile B. Notice that we are just looking for a matching of A. Each value needs to be found in the piles exactly once. Now I've prepared that for us in Sketchpad. There's our 13 cards ranging from ace to king. Here's the cards stacked in suits of 4. There's 4 suits in a pack of 52 cards, excuse me. So if I look at this, folks, you could see there's one line that or edge that leaves every vertex at the top. So, and there's one that enters every vertex at the bottom. So this looks like it is indeed the case. If this is set A, I cannot find a subset of A which violates my condition that the neighborhood must contain at least the amount of elements in that subset. Well, it contains exactly the amount of elements. So it looks like this is true. But let's now just talk about how we're going to prove this. We will have a matching if the matching condition holds. In other words, if this holds. Given any set of card values, a subset S of the set A, we must show that this is true. Now we've seen it in the graph. Well, that is, if the number of piles that contain those values is at least the number of different values. But what if it isn't? So let's say the cardinality of the subset is K. If the neighborhood is less than K, then we would have fewer than 4K cards in each of those piles, since each pile will contain 4 cards. There's 4 suits. But there are 4 cards with a different K values. So at least one of these cards must be in another pile, which is a contradiction, because we piled the values on top of each other. Thus the matching conditions hold because of that contradiction, and there is a matching as was required. Okay, I'm going to look at 1, 2, maybe 3 examples now where we work with our condition and see how it works. Okay, so let's have a look at my first example that I've got ready for you. The first one, we're looking at the matching of bipartite graphs. The question is, does the graph have a matching of size 4? Now remember, it will have a matching of size 4 if those conditions have been met. So what do we notice here? Set P's cardinality is less than the cardinality of Q. So we're going to deliberately pick set P as in our problem with students and topics as the students, and set Q will be the topics that is chosen, so that we at least have a starting point of the neighborhood of S. The elements, there's 5 elements in the neighborhood, there's 4 elements in the S values, so already NS is bigger than S. So let's see if this is possible. Can we, in other words, now find a subset of S that violates the Hall's marriage principle, where the neighborhood is less than the subset. Let's have a look. If we look at vertex A, it has a neighborhood of 3, so NS is bigger than that. If we look at vertex B, it has a neighborhood of 1. If we look at vertex C, it has a neighborhood of 1. But notice that the set BC, which is 2 elements, the subset, goes to 1 element in the neighborhood. D doesn't have a problem. 1 vertex going to 2 neighborhoods, so NS is bigger than S. So we've seen that if we choose S, which is a subset of P, then N of S will be a subset of Q. So let the subset S that we choose be BC. Then its neighbor will have 1 element, and that's the vertex 3. So that violates Hall's marriage theorem, because the neighborhood contains less elements than what S contains. So the graph does not have a matching of size 4, based on the fact that Hall's theorem has been violated. Let's look at another set. We're asking, does this graph have a matching size of 5? Now let's just go through each vertex. Vertex 1, before we go there, you can see in this case the 2 vertex sets have the same number of elements. So we can really pick one of the 2 as set S, and the other set will then be the neighborhood of S. So we're going to start by looking at set P, because the cardinality of P and Q are equal. Set P will be our S values, and set Q will be our S values. So here's our S values, there's our neighborhood of S. So let's start from this side. A has 3 neighbors, so NS is bigger than S. The cardinality of NS is bigger than the cardinality of S. Here we have 1 going to 2, so that is satisfied. Here we have 1 going to 2. Here we have 1 going to 2. Now what's interesting is that all 3 of these are going to the same 2 vertices. Okay, so that's a problem. We have found a subset BCD that contains 3 elements, where its neighborhood contains only 2 elements. So again, the cardinality of the neighborhood is 2, the cardinality of the set S is 3, which violates Hall's marriage theorem, and therefore no, this graph does not have a matching of size 5. Okay, let's return to the sets and swap them around. So now the top set is my set S, and their neighbors is found in set Q. Now let's have a look. Vertex 1 maps onto 3, which is fine, NS is bigger than S. Vertex 2 maps onto 2, NS is bigger than S. Vertex 3 maps onto 3 other vertices. That means that for that vertex it's fine. Vertex 4 maps onto 2 other vertices, which means NS is bigger than S, and the same goes for vertex 5. But now look at what happened. Vertex 2 goes to A and E, vertex 4 goes to A and E, vertex 5 goes to A and E. We have a problem, Houston. There are 3 elements in set S, and the neighborhood only contains 2 elements. So again it violates Hall's marriage theorem. The cardinality of NS is 2, the cardinality of S is 3. So yes, confirmed, if the sets are swapped around, it still does not have a matching of size 5. Okay, I hope it starts making sense to you. Let's revisit our very initial graph that we found on our first page, which was the graph on page 283, the investigation graph. Again, we're sitting with a situation where the 2 vertices are indeed equal. Okay, so we're going to choose any set as my set S. I'm choosing the subset S to come from the top vertices P, so the neighborhood would come from the bottom vertices. So let's run through it once. Let the subset be A. A maps onto 3 elements in the neighborhood. So that is true and we are happy with that. Subset B maps onto 2 elements, so we're still happy. N of S is still bigger than S. Can be bigger than or equal to. Remember, that's Hall's marriage theorem's condition. Okay, SC maps onto 3 and 5, which is 2, so it's still bigger. Set D maps onto 3 elements. Set E maps onto 2, and set F maps onto 3 elements. So right through from every single vertex, if we now look at those vertices here, they don't repeat. So no vertex in set S has the same neighbors. So there is no problem for us. We definitely have the condition of Hall's theorem respected and met here. So this graph does have a matching of size 6, which we saw at the beginning of our video. Okay, so what are those sides? So let's pick them. A1, B3, C5. So that means I'm matching A with 1. I'm matching B with 3. Matching C with 5. Matching D with 2. Matching E with 6. And matching F with 4. I've used every vertex in the top set once, and every vertex in the bottom set has been used once and once only. Okay folks, that concludes our discussion of the matching in bipartite graphs. Make sure that you go through the work at the end of that chapter, and straight after that is the chapter summary with quite a few problems that you can work through. Indeed, there's 22 problems to work through in the chapter summary. It takes the chapter, as you know, and everything that was studied in the chapter is contained in the 22 or 23 questions in the chapter summary. Remember to like the video if you liked it, subscribe to my channel.